Hi, my name is Hussam, and I will be presenting our paper Instance-Aware Multi-Object Self-Supervision for Monocular Depth Prediction. Self-supervised depth prediction is one of the most successful and supervised learning. It uses image reconstruction as a pretext task. In a basic pipeline, a pose and the depth are learned from an image sequence and a warping function is used to reconstruct the image. A common assumption of this warping is a rigid scene, that is a static scene and a moving camera. When supervised with monocular video, this assumption is violated due to the moving objects. In this work, we address the problem of moving objects in the scene and we alleviate the rigid scene assumption. We propose instance-aware multi-object self-supervision for monocular depth prediction. Our method addresses the problem of dynamic objects by predicting a 6-degree of freedom pose for each dynamic object in the scene. This is done using a novel architecture that extends panoptic segmentation network with object poses. We achieve a competitive performance compared to the state-of-the-art, and we address further the bias of Kitty dataset to our static scene, and we provide a better approach to evaluate the depth. Before deep diving into our method, we give a small review on how the prior work handled moving objects. First, we have the method that masks moving object, and surprisingly, these are the state-of-the-art. They rely on masking the dynamic objects. This technique is simple and easy to plug, and we will see later why it is the case, why these methods are the state-of-the-art. Second, optical flow-based networks. Uses optical flow to address the motion, however, it does not explicitly model the rigid movement of the objects. We have also other methods that use component clustering, and these methods cluster the scene into components and predict the motion of these components. In order to alleviate the static scene assumption, we propose to disentangle static and dynamic objects using a global rigid scene pose and a piecewise rigid pose for each dynamic object. An instance segmentation network is extended to incorporate the pose information so that the network learns the additional 6-degree of freedom for each instance. Therefore, each instance I is represented by its class Ci, bounding box, and mask, and the additional pose. The objective is to warp the source images into the target images using the depth and the poses. This inverse warping is defined as: first, we backproject the point using the camera parameters and the learned depth. We apply the ego pose transformation. If the point belongs to a static object, we use the identity. And if a point belongs to a moving object, we use the object pose. We do this for each object. And finally, we project the 3D points to the image reference. In our case, the source images are I of t minus 1 and I of t plus 1, and the target images is I of t. Similarly to the prior work, the supervision is done using photometric loss and depth smoothness. The proposed model architecture consists of efficient panoptic segmentation network extended with a novel instance pose head, an ego pose head, and the depth head. During training, the FPN features are extracted for the source I of t and the target frames I of t minus 1 and I of t plus 1. These features are pooled using the proposal of the RPN and the RU-align module. The novel instance pose head is a transformer network that performs spatiotemporal correlation of the features, which enables learning the matching and the interaction of the object instances. This head outputs 6-axis angle parameters for each instance. And similarly, the ego pose head outputs a 6-axis angle parameters for the ego pose. The depth head input the FPN features of the source frame I of t and output a multi-scale depth. The output of this network is multimodal covering depth, semantic, instance, and the poses. We achieve competitive results compared to the state-of-the-art on Kitty Eigen benchmark. We outperform all the prior networks that handles the moving object, such as NSTUDYM, monodepth, SEG, and competitive collaboration. The current state of the art are the methods that masks dynamic objects during supervision. In contrast to training, where the points are categorized into moving and static object points, evaluation is performed on the mean of all points. It is not possible to convey how the model performs on moving objects. We have analyzed further the results and we found that more than 86% of the evaluation set points are static. This shows that the current evaluation is biased towards static objects. Masking moving object method have the advantage in this dataset as they exploit well this bias by training only on static objects. And therefore, we propose to disentangle static and dynamic points during evaluation for better assessment of the depth. The per category mean catches better the performance on both static and dynamic objects. As observed in the table, our method outperformed the state-of-the-art many depth for dynamic objects and per category means. We compare also to our direct competitor NSTUDYM, and we can observe that we outperform this method on nearly all metrics. We show a qualitative results of the proposed method versus the current state of the art. As observed, our method have more consistent depth for moving objects than the baseline, and moreover, our method does not degenerate on static objects. We show also the generated point cloud across a sequence of images, and as observed, the depth is accurate and temporally consistent. Please check out our paper for more details. We will be happy to receive you at our poster to discuss further. Thank you.